Hi students, in this video we will discuss about Dirichlet conditions and Gibbs phenomenon. In the previous video about continuous time Fourier series, we have learned that any non-sinusoidal periodic signal can be expressed as a linear combination of harmonically related complex exponential. However, some questions remain. In fact, these questions were one of the major opposition against Fourier's work when he tried to publish it. Is it possible to synthesize discontinuous signals using smooth sinusoids? We know that smooth signals can be synthesized using sinusoids. But what about signals like square signal, which has sharp rising and falling edges unlike the smooth signals? Is it possible to synthesize such discontinuous signals using Fourier series? It is equivalent to asking the question, is it possible to make a knife using feathers? Another question is that, is it possible to synthesize all kind of periodic signals using Fourier series? These questions remained in the thoughts of mathematicians after Fourier presented his original idea. In the year 1829, German mathematician P.L. Dirichlet published some conditions for the existence of Fourier series of a signal. This is famously known as Dirichlet conditions. Also, a strange behavior of the square signal, which basically satisfy the Dirichlet conditions when expressed using Fourier series studied by the famous American mathematician J.W. Gibbs, and this is known as Gibbs phenomenon. We are going to learn about these concepts in this video. Before going to these concepts, we must analyze the concept of convergence of Fourier series. Consider approximating a periodic signal x of t using a finite number of harmonically related complex exponentials. For theory, we can have infinite number of terms, but in practice, we may have to restrict to a finite number of terms for ease of computation or storage or representation. That means instead of an infinite number of harmonically related complex exponentials, we are considering only finite, that means n number of harmonically related complex exponentials. This is known as truncated Fourier series. Here the original signal and the signal synthesized using truncated Fourier series are given. X of t is the original signal and xn of t is the signal synthesized using the truncated Fourier series. Let the error between these two signals be E of t. We know that x of t is the original signal and xn of t is the synthesized signal using n number of harmonically related complex exponentials. So of course there will be some small error because both of these signals are not equal. So this error is equal to E of t. In order to measure the accuracy of approximation, we need to use a quantitative measure to check the size of the error. The measure we use here is the energy of the signal. We can see from the above result that energy becomes 0 when n tends to infinity. That means when we use an infinite number of terms, the energy becomes 0 and both the signal x of t and xn of t become equal. This is a good measure of our approximation. That means how many number of harmonically related complex exponential need to be used to make the energy 0. Now we have the analysis and synthesis equation of CTFS given like this. In the case of some signals, this integral, that is the analysis equation integral, may diverge. That means the value obtained from this integral for a particular ak value will be infinite. Sometimes when we substitute the coefficients obtained through this analysis equation into our actual synthesis equation, that series may converge or sometimes that series may diverge. For a large class of practical signals, there is no problem of convergence exist. But in the case of some signals, there is a problem of divergence. Using the above ideas, we can conclude that a signal x of t to be represented using Fourier series, it must have finite energy over a single period. That is mathematically shown here. This condition says that the energy of a periodic signal over a single period must be finite. Now let us learn more about Dirichlet conditions. P.L. Dirichlet provided the rigorous mathematical analysis for the Fourier series and put forward a set of conditions for the existence of CTFS. This is known as Dirichlet conditions. Condition 1. Over any period, x of t must be absolutely integrable. That is, integral t x of t dt must be less than infinity. This guarantees that the CTFS coefficients ak will be finite. A signal that violates this condition is x of t is equal to 1 by t between the range 0 to 1. This signal is illustrated here. You can see that this is a periodic signal. However, this violates the first condition of Dirichlet. This is because it has an infinite value at the beginning of each period. Thus, if we find the area under the curve, it will not be a finite value. Hence, it is not possible to represent this signal using Fourier series. Condition 2. In any finite interval, x of t is of bounded variation. There are no more than finite number of maxima and minima during any single period of the signal. An example of a signal that meets condition 1 but violates condition 2 is x of t is equal to sine 2 pi by t in the range 0 to 1. You can see that this signal is also periodic. Also, it satisfies the condition 1. However, it has infinite number of maxima and minima. That means the positive peaks and negative peaks within a single period. Hence, it is not possible to represent this signal using Fourier series. Condition 3. In any finite interval of time, there must be only a finite number of discontinuities. Furthermore, each of these discontinuities should be finite. An example signal is given here. This signal has a period t is equal to 8 is composed of an infinite number of sections, each of which has half the height and half the width of the previous section. Thus, the area under one period of the function is clearly less than 8. However, there are an infinite number of discontinuities in each period, and because of that reason, this is violating the condition 3, and hence it is not possible to represent this signal using Fourier series. So these are the Dirichlet conditions. Now let us look at Gibbs phenomenon. In 1898, an American physicist, Albert Michelson, constructed a harmonic analyzer, a mechanical device that for any periodic signal x of t would compute the truncated Fourier series approximation as per this equation. First, let us watch a video about the working of Albert Michelson's harmonic analyzer and come back to the Gibbs phenomenon.
Albert Michelson's harmonic analyzer. This 19th century machine adds together cosines to create intricate patterns. Amazingly, it also does the inverse operation. It can take a pattern and reveal the cosines that when added together will approximate it. This operation is called Fourier analysis and is possibly the most important mathematical technique of the past 100 years. Without Fourier analysis, there would be no MP3s, JPEGs, or cell phones as we know them today. To celebrate this stunning machine and to gain a greater insight into what Fourier analysis is and how it works, I'll share in this video some history of this analyzer. This machine's designer, Albert Michelson, was famous for measuring the speed of light, yet he also measured many other properties of the universe precisely, like the diameter of stars or the rigidity of the Earth. In the late 19th century, he performed Fourier analysis by hand to help resolve fine details of the light emitted by vaporized elements. He was doing an early version of Fourier transform spectroscopy. These hand calculations were laborious, so he invented this machine to automate these calculations. He built a prototype machine similar to this one in 1897, and then a larger prototype 4 times the size a year later. The machine was then commercialized by William Gartner and Company. They made precision scientific instruments often designed by Michelson. In their 1904 catalog, they advertised this machine, which can add up to 20 different sinusoids, as well as a larger version that calculated with 80 sinusoids. We know that in the early 20th century, Gartner sold at least 4 of these machines, and based on that, it seems this 20-element machine sold for around $225, and that it was likely made between 1901 and 1910. After this period, the machines are mentioned only occasionally. We found pictures of several different configurations until it made one last public appearance in an improved form at the 1933 World's Fair in the Great Hall of Science in an exhibit called The Magic of Analysis. This astonishing machine uses just gears and springs to add together sinusoids. This synthesis, as it's called, creates beautiful patterns that look nothing like sinusoids. The machine produces patterns like beats, smooth peaks, sharp corners, or even jagged edges. And these can all be made using this function. Here's how this mechanical marvel implements that function. The machine has 5 key sections. First, a crank that varies x. Second, gears and cams that generate frequencies. Third, just a little bit above that, rocker arms that create the sinusoids, and amplitude bars to weigh those sinusoids. Fourth, at the top, springs and levers that add together these weighted sinusoids. And lastly, on the front side, a mechanism for recording the sum on a piece of paper. At the heart of the machine lies 2 sets of gears. This cone-shaped set has 20 gears that vary linearly in both size and number of teeth. It engages this cylindrical set of 20 gears, all of the same size. Watch what happens as I turn the crank. The gears on the cone-shaped set all rotate together. The gears on the cylindrical set can rotate independently, each at a rate determined by the corresponding gear on the cone. This gear rotates twice as fast as this gear, this one 3 times as fast, and so on. These gears generate the different frequencies. A cam on each gear drives the rocker arm up and down via a connecting rod. As each gear rotates, the corresponding rocker arm traces out an up and down or a sinusoidal motion with the same frequency. For example, the first rocker arm oscillates to produce cosine 1x, the 10th produces cosine 10x, and the 20th cosine 20x. Of course, the arms in between produce cosine 2x, 3x, 4x, and so on. At the bottom, a series of long vertical bars rest on each rocker arm. At the top, these bars attach to levers that are spring-loaded. The position of the rocker arms on the bar determines the coefficient. As I slide this bar to the edge of the rocker arm, the lever at top rises. That's a coefficient of +10. When I return it to the rocker arm's pivot, the lever returns to its original position, a coefficient of 0. And as I continue to slide to the opposite edge, the lever drops, a coefficient of -10. Now, let me show you how the machine sums these sinusoidal motions weighted by their coefficients. I'll set the machine up to produce beats using sine 12x and sine 10x. Each lever at the top of the machine has a spring that connects it to a pivoted bar. A large spring balances the pole of the series of springs on the levers. If we look at the top, we see the spring extends more than a foot above the machine. As I turn the crank, the amplitude bars drive the spring-loaded levers up and down. This in turn moves the pivoted bar. Because the springs all pull on the same pivoted bar, their displacements are summed. If we take a close look at the pivoted bar, we see that it sweeps out a small arc. We can barely see it go up and down. Let's return to the front to see how the machine amplifies this motion and then records it. This lever magnifies the result from the summer, but it's still a very small motion. A wire connects the magnifying lever to a set of concentric wheels that amplify further the motion. This wire pulls on the hub of this inner wheel, while a different wire is wrapped around the outer wheel. The wire attached to the larger wheel moves the pen vertically as a set of gears connected to the crank has been moving the paper horizontally under the pen. This is the same crank that rotates the gears to create the sinusoids and that also moves the pen up and down. In the previous video, I showed how turning the crank on this machine generates 20 different frequencies, also known as harmonics, which are turned into cosines here, multiplied by coefficients, then summed, magnified, and the resulting function plotted here on the front. This process is called synthesis. But this machine is called a harmonic analyzer, which means it can be used to solve the much more difficult inverse problem called analysis. For example, if I want to plot a particular function here, how do I set the amplitude bars to produce it? To illustrate how this machine does analysis, let's start with a square wave. First, we use some unique properties of the square wave. Since it's periodic and even, all of the information that function carries is contained in half a period. So we'll take that half a period and sample it at 20 equally spaced points. We use the values of these points as the inputs for the machine. When we turn the crank, we produce a new function that reveals the correct coefficients. To see how we get these coefficients, we'll look at the side of the machine. As I turn the crank, the tips of the rocker arms form a sinusoid. The indices on the rocker arms run from high on the left to low on the right. I'll flip the video to make it a little more intuitive. When the rocker arm tips are lined up in a straight line, we'll call that crank number 0. If the horizontal axis runs from 0 to pi, and the vertical axis from -1 to +1, then we can describe the position of the rocker arms with a cosine. Every 2 turns of the crank increases the frequency of the cosine by 1. At these even numbered cranks, the values of the function on the platen yield the coefficients we're looking for. Let's rewind and watch the plot and the rocker arms simultaneously. If we pause briefly at every second crank, a point is marked on the function. We create a total of 20 points. If we look at the output from the machine and compare it to a sync calculated by a computer, we see that they are very similar. Now, we'll take the data points from the sync, scale them, and use these values on the rocker arms. Remember that our goal is to program the analyzer so that it will plot a square wave. Now, as I turn the crank, the pen writes a horizontal line, then drops and writes another flat section, which amazes me because we're adding only cosines. And then it rises to write another horizontal line. Of course, what we're seeing is a square wave. What I've just shown with the machine is an essential feature of Fourier methods. I can take a function, perform harmonic analysis, extract the coefficients, and then synthesize that function to approximate the original.
So this harmonic analyzer, constructed by Albert Michelson, had the capability to create truncated Fourier series approximation using up to n is equal to 80 terms. Michelson tested his device on many functions with the expected result that xn of t looked very much like x of t. However, when he tried the square wave, he obtained an important and very surprising result. Michelson was concerned about the behavior he observed and thought that his device might have had a defect. He wrote about this problem to the famous mathematical physicist Josiah Gibbs, who investigated it and reported his explanation in 1899. What Michelson observed has illustrated in this figure. Here, red color indicate the actual square signal and the blue color signal indicate the synthesized signal. You can see that when n increases from 1 to 70, our approximation is almost equal to a square signal, but there are some problems. The interesting effect that Michelson observed is that the behavior of the truncated Fourier series in the vicinity of the discontinuity, which exhibits ripples, and that the peak amplitude of these ripples does not seem to decrease with increasing n. For a discontinuity of unity height, the truncated Fourier series exhibit a maximum value of 1.09. That means an overshoot of 9% of the height of the discontinuity. This series converges pointwise at all points except the discontinuity of the signal x of t. It is precisely at these discontinuities that the series differs from x of t by 9%. As n increases, the ripples in the partial sums become compressed towards the discontinuity, but for any finite value of n, the peak amplitude of the ripples remains constant. This behavior has been known as the Gibbs phenomenon. Abrupt truncation of the continuous time Fourier series for ease of representation, ease of storage, or ease of computation is a reason for Gibbs phenomenon. The truncated Fourier series approximation xn of t of a discontinuous signal x of t will in general exhibit high frequency ripples and overshoot near the discontinuities. This behavior is known as Gibbs phenomenon. I hope the idea of Dirichlet conditions and Gibbs phenomenon is clear. Thank you for watching.